we had been discussing various machine learning methods for which we discussed is important for feature selection, and like in the context of economics, we also discussed that these feature selection methodologies are useful for for causality. That is to say, for like if we have an observation and or a phenomena we are observing and we are interested to understand what are the causes for it, then we have been discussing some methods, some techniques which help us to identify those potential causes. So, or I mean, identify the important causes out of the like a large list of potential causes. So, can anyone recapitulate briefly? That is, what methods or related to machine learning we have covered in the last couple of classes? Anyone remembers? Ashwin Tripathi, what were some of the machine learning methods we studied? Ashwin Tripathi, we can't hear you. What about Ananya Parikh? Can you? Yes, Ashwin, can you answer? Ananya Parikh, can you answer the question?
Hello.
Yes.
Yes, sir. Sir, we studied about the lasso regression, where we use the lambda parameter with the function, which was used to decide whether uh, like the uh, like we were to reduce the weights of the features that we were using. So for the same, if the weights were higher, then the f function was also higher. Likewise, if lower, and the lambda we used it for balancing it. And
Right.
the thing was the decision trees. We aimed at increasing the information gain.
Right. Very good, Ananya. Thank you. Uh, so like as Ananya said, we were our aim was to that is our aim was to identify out of a large number of possible predictors or features, our aim was to identify a small number of them. So we were using this algorithm known as lasso. What lasso does is to identify a small number of variables by making sure that the remaining ones, their coefficients become close to zero, so that only the most important ones, they remain and they get selected. So that is the about lasso regression. But we also discussed that lasso regression has a failing, due to which it often does not work well under certain conditions when we are looking for causality. That is to say, for the feature selection problem in machine learning, lasso may be great, but when in the domain of economics, when we are like in a certain condition, lasso may not be the best option. That is, it may give wrong results. In such a situation, we have to go for a modification of the lasso algorithm. So does anyone want remember under what circumstances lasso does not do well, and what we do to, or how we modify lasso to get around the problem? Sunidhi, you want to answer? Sunidhi, do you remember like how under what conditions lasso fails when we are looking for causal relationships? Swapnil Bhomik, can you answer?
Sir, I did not attend last class.
Okay, did not attend. Gyanoranjan Pradhan, do you remember?
Yes, sir.
Anyone else? Anyone wants to volunteer to reply under when lasso does not do well for causality detection?
Sir, it is not differentiable at 0, so there might be an issue over there because
No, that no, no, that
L1.
is no, that is not the answer I am looking for. That is a general problem with lasso, but specifically when we are looking for causality analysis, then what is the like what is the problem which that is why does when does lasso give wrong results? Specifically in the context of causal factor detection. Abhishek Kumar Singh, you want to try? Pankuri?
So lasso regression, like maybe the coefficients could like become too small, and so some.
True, but that's a general thing. But specifically in the context of uh, causality detection, so does anybody remember the term called confounders? What's confounder?
If a factor determines the outcome of two similar things, like
that is to say, like suppose we are trying to look for, like suppose there is an effect y which we are trying to for which we are trying to look for causes, and we have a set of potential causes, and then the factors which we are considering as potential causes, some of them themselves are interrelated. That is to say, confounder. So confounder is basically some factor which influences both the cause and the effect. So if we have like a set among the different things which different factors which we are considering as potential causes for the effect that we are focusing on, if those are themselves related to each other, then there is a problem, and then under such situations lasso does not do well. So what is the modification of lasso which we discussed in both the last lecture and the lecture before that? Anybody remembers? Did we not discuss something known as double lasso?
Using L1 instead of L0 now.
Sorry, you are not audible, Gyanaranjan.
Sir, we used L1 instead of L0.
L1, that is lasso regression, but so lasso regression we have already discussed, but what is double lasso? Does anyone remember?
Sir, we used a treatment parameter above the lasso regression, sir, but I was confused why it was used basically. If you could repeat that.
Okay, so in that case, so let us go back to the lasso regression. So this is the double lasso formulation. So what happens in double? So let us read once again. So consider a regression model with treatment parameters and control variables on the right hand side. The number of potential controls is large, potentially even larger than the sample size. So what are the controls? the controls are basically so basically like whenever we are studying any kind of economic problems, so suppose that like we are looking, let us say that there is something something which we are trying to measure. So we'll see some examples of this in today's class also. So suppose that is so suppose we denote whatever we are trying to measure as y, and it's the various factors which potentially control that thing, that variable, I mean y. Let us denote them by this x1, x2 up to xp. And so let's say that p is a very large number. That is to say, these are the list of possible causes for the effect which we are trying to measure. Okay? And what we really want is we want to select a relatively small number of regressors that really matter. That is these are all, most of these are only potential causes or potential controls, as they say in the lingo of economics. Out of them, only a small number of them actually matters. So that is what we are trying to find out. Okay, so that so one way to do it is through lasso regression, as was already discussed. But the problem is that if there are confounders, that is to say, if some of these are themselves related to each other, then the lasso regression fails to give useful answers. In such a situation, what we do is we go for a double selection procedure, or what is sometimes known as a double lasso or a double machine learning approach. So what it basically says is, first step, select the predictors for outcomes y using lasso. Right, so this is straightforward enough. This is a normal lasso. After that, select predictors for the treatment status di using lasso. So what is treatment status? So suppose that okay, before understanding this in a bigger detail, let me introduce you a new concept. This new concept is known as randomized control trials, or RCTs. So those of you who are from economic background, I'm sure many of you have heard of this. So what is this randomized control trials? Does anyone want to volunteer and tell?
So in this, basically the population is divided into two groups randomly, and then like there is a treatment, some kind of like in case of economics, it might be like a policy treatment or like some aid provided to a village or something that is only given to one of these groups. And then basically the impact is seen across the groups to those who were given the treatment and those who were not given the treatment.
Exactly. Thank you, Makuri. So so basically, so what happens in case of a randomized control trial is that we have a population like this. Now, what is to be done is that the population, that is now what we are interested in, that suppose we want to understand, suppose we have a problem at hand. So let's say that we want to understand, for example, that if let us take a like a very contemporary example. Suppose I have a vaccine for coronavirus. I mean, I have a vaccine which claims to cure coronavirus. So then I want to test whether it actually works or not. So what will I do? So what can be done is that the entire population is to be split into two random groups. So some people are here, some people are here. Okay. So in this case, that is to say, I have two things which I am primarily interested in. One is the variable, or what they call as the treatment. What is the treatment in this case? The vaccine. And let's denote the treatment by X. And then so this treatment, basically, let us say it is binary. That is, either it is given to a person or it is not given either. Or if you want to say, let us say it takes three values, 0, 1 and 2, means not given at all, 1 dose given and 2 doses given. Okay. So so now what we are and like this is the treatment variable, and then there is the effect. What is the effect? The effect is whether COVID is like whether COVID happens or not happens. I mean, not exactly happens or not happens, but that is the rate of COVID infection high or is it low? Is it higher than average or is it lower than average? Let's put it this way. Okay. So now what is to be done? We divide the population into two groups. One or in this case three groups. So in each, the first group is given no dose of the vaccine at all. They are not treated with that vaccine. That is to say, for them the input, the treatment variable X takes the value of 0. For the second group, which so that group we sometimes called as the control group. So that is the group which is behaving in the natural way, normal way. That is, we have not done any intervention on it. Next, we have another group for which X equal to 1. That means it is group is given one shot of the vaccine. And then the third group is for them X equal to 2. That is, their people there are given 2 shots of the vaccine at the prescribed interval. Now, so basically there are two groups which undergo the intervention. One is that group which for which X equal to 1, they get one kind of intervention. The other is the X equal to 2, they get another kind of intervention. And lastly, there is the control group who do not receive any intervention. Okay. Now what happens is that we separately measure the outcome separately in all the three groups. Now it may happen that like in the control group, let us say the control group size is say like 10,000 people or something like that. It has to be a reasonably large sample size. So suppose we find out that the prevalence rate or the COVID infection rate among these people the control group who did not receive any shot of the vaccine is about 30%. That is, 30% of those people catch COVID. If you look at the second group, we see that that for whom who have received one shot of the vaccine, it's found that the COVID prevalence rate is 32%. And the third group for which X equal to 2, we find that the COVID prevalence rate is 15%, 1-5. Okay. So on the basis of such an experiment, what can be said? Yes. Anyone? Please respond. Otherwise, this class will not have any meaning. Suppose there are three groups of people, like who have, did you understand the question? There are three groups of people. One of them did not receive any intervention at all. That is, they received 0 doses of vaccine. And among them, the COVID prevalence rate was found to be 30%. Among the second group of people who received 1 dose of vaccine, that is X equal to 1, among them the prevalence rate is 32%. And finally, for the third group of people for who received 2 doses of vaccine for which X equal to 2, for them the prevalence rate is 15%. So from such an experiment, what conclusion can be drawn?
What do you mean by prevalence rate?
Let us say that among them 30% people have people have caught COVID. After that is, we let those people work around normally for a certain period, for an observation period of 2 months or 3 months, and we see that in each of the group in the first group 30% of them caught COVID, in the second group 32% caught COVID, and in the third group 15% caught COVID. Then what can we say?
Sir, we could say that having 1 dose of the vaccine doesn't do much, but if somebody has taken 2 doses, it significantly reduces the chances of getting COVID.
Exactly. Right. So that means what? That means that that is we can now okay, fine. So what you said is definitely right. It suggests that the group of people who received 2 shots it seems that like they are getting significantly less chance, that is they seem to be having significantly less chance of infection compared to the other groups. Okay, but here is a very important catch. The important catch is that among all the three groups which we are considering, or if it is among all the groups of people which we are considering, all other factors except for the treatment has to remain the same. Right? Like for example, if it happens that the first group of people are mostly say like daily wage earners or like laborers who and the first group of and the third group of people who have got the 2 shots, they are mostly software engineers, then we probably will that is the conclusion which we have drawn may be wrong. Why? Because the daily wage earners in the first group, they have to go around, they have to like that is they cannot work from home, they have to go around every day, they have to travel by public transport, they have to go to their workplaces, they have to mingle with so many other people, while the software engineers, they have the luxury of being able to work from the safety of their homes. So if the COVID infection is less among them, it may be less, we cannot be sure that it is really due to the vaccine, it may well be due to the simple fact that they interact less among themselves, so that there is less contact, right? While that's not true for the, or the reverse is true for the first group, or maybe even for the second group. Okay, so that means what? That means that suggests that whenever we have to do a randomized control trial, we have to make sure that all the populations into which we are dividing the original population, they must be identical in every respect other than the treatment, right? So why do we say randomized control trial? What is the significance of the words randomized and controlled? So that is what is indicated by these things. Why randomized? Because we divide the people into groups randomly. It has to be absolutely randomized. And that is to say there should not be even any kind of bias which suggests that one of the groups is different from the other groups. Okay, so this like basically this is known as the randomized control trial. Now let us come back to the question which we are studying earlier. So the question of treatment. Okay, so like as I already said, that there are a large number of controls. So all the factors that we did not consider but could have played an important role behind whether this COVID is spreading among the different populations or not, let us consider those as let us call those as the controls. So those controls might be that is the daily number of people or the daily number of contacts they have, or that is whether they are wearing mask all the time or not, or or maybe their age and comorbidity, etc., etc. So all these factors, these can be potential controls, or like whether they are taking other kinds of medicines or not, those also can be potential controls. Okay, so these are basically, we do not know whether they impact the final result or not. What is the final result? Whether people are getting COVID or not, whether people are getting infected or not. So it's possible that several of these factors also have an impact. Okay, but that is not what we are, but what we are really interested here is in a particular factor, whether they are receiving my vaccine or not. Okay, so that is, so that vaccine, that is what we call as the treatment status, DI. So that is so there are so many possible causes of getting COVID, or getting or not getting COVID. One is the status of the vaccination, and like which I call as DI, and that I call it as the treatment. And apart from that, all other factors, there, let us say there are P factors, I have kept them together and denoting them by x1, x2 up to xp, and I'm calling them as potential controls. Okay, so now the question arises whether this, that is the question which I am trying to answer here, is whether this DI is an effective treatment for COVID or not. That is to say, for certain values of DI, all other factors remaining unchanged, is Y an important factor, that is Y affected or not? Okay, that is a question. Now, it may happen that this treatment DI itself is affected by some of these factors. That is to say, whether a person is vaccinated or not, or receives the vaccine or not, may be decided by, or maybe at least impacted by, some of these other factors which may be causing the COVID. Say for example, their income. So if their income is quite high, so that can affect both XI. I mean, it can affect both DI and YI. Why? Now, because if income is high, that means they probably have a greater access to the vaccine. They can they can afford to travel to the vaccination centers. They can afford to buy the vaccine, and they can afford to get themselves vaccinated, etc. On the contrary, that factor, their economic or their income can affect their YI also. I mean, if they are rich, then it's possible they do not need to travel so much to crowded or to risky places. They can stay at home and work, and so in that case, of course, they will have a lesser chance of getting infected. So so what I am suggesting here is that this particular factor, let us call that as X5, which stands for their income, is a confounder because it is impacting both the treatment DI as well as the outcome YI. Okay. So if there are indeed confounders like this which are impacting both the treatment as well as the outcome, then our lasso will not be able to do a good job. That is what I actually want from lasso. As was already discussed, what lasso does is it tries to remove most of the useless factors and focus only on the useful factors. So that means if this vaccination is an useful factor and all other factors are useless, then we expect lasso should give a non-zero coefficient against DI, and it should give a nearly zero coefficient against everything else. Okay, but if it happens that this X5 is a confounder which impacts both DI as well as YI, then running a lasso may not be able to give me the it may not be able to pull out the effect in the way we want to. Okay, so in fact, I will consider giving you an assignment also on this after this. So what people do is they do double lasso. That is to say, first they try to express the outcome YI, that is to say whether they are getting COVID or not, as a function of all the factors including the treatment. So so note that this ZI, what they have written here, this ZI basically indicates the collection of all the factors which like all factors which we have, all the potential factors which we have, which may be affecting YI, and apart from that it also includes DI. Okay, so this alpha naught is basically is a coefficient of this particular thing DI, I mean the coefficient of the treatment. Similarly, this what they are calling as GZI, this GZI is actually can be written in this way. That is what, so this is like X. What is Xi prime? Xi prime is the set of or the vector of all these observations. So, and beta, what they are calling as beta, is nothing but the set of their corresponding coefficients. So this is basically the linear representation of that is the linear representation of the observation YI expressed as a linear combination of all the possible causes, which includes the treatment DI. The treatment is written separately because we want to give we want to understand it clear separately, and apart from it we also have the other potential factors about which we are not sure. Okay, so this is one equation, or this is one formulation which we make here. The other formulation which we make here is di, we try to express it in terms of the other factors. So that is di is what? Di is the treatment. So here what we are trying to do is basically we are doing in two steps. One is one is we are trying to express the observed variable or the effect, so to say, as a linear combination of everything, including the treatment as well as the potential causes. And in the second case, we are actually expressing the treatment itself as a linear combination of the potential causes. So here this is being done, this kind of a differentiation is being done precisely to identify the these things, what you say, the confounders. So that is, if some of the potential causes are actually impacting the treatment itself, then that should be brought out by this equation. And then whether among the, and this equation basically brings out the impact of the treatment as well as the other potential causes for on the yi. Okay, so this is the formula. So this is to be solved using a lasso. This is also to be solved using lasso. As you can see, both of these are linear regressions. Now lasso regression is, as we have already discussed, lasso regression is achieved by putting a potential like a loss function, a L1 loss function on the linear regression problem. So in both of these cases we can do that thing. Okay, so and now is this clear, the concept of double linear double lasso?
Yes, sir. Yes, sir.
Okay, good, fine. So this is what we call as the double selection lasso. So yes,
Why this double lasso actually works?
why it actually works? So basically that is what single lasso or not usual lasso does is like it help that is, if you have a large number of parameters or potential features, what single lasso does is it tries to make most of these coefficients as 0. Okay, so the what are the, suppose this thing is not there, suppose this equation 4 is not there, only equation 3 we are solving using lasso. That means what, when we so what are the coefficients here? Alpha naught as well as the all the betas. So what single lasso or usual lasso does is it tries to make most of these things, most of these coefficients as 0 or something close to 0, so that they can be disregarded. But like as I already said, it has, like through observations as well as through various theoretical studies which will not go into, it can be shown that if there exists a linear regression among the a linear relationship among these predictors themselves, then the result which lasso gives is not a good one. That is, it will not be able to identify those things or those factors which are useful, and it will filter out the ones which are useless. It will get confused. So in fact, we will I will try to set you an assignment to explore this yourself. On the contrary, what is happening in double lasso is we are actually clearly trying to bring out that effect by expressing the treatment di itself as in terms of the other variables. So we are, and here again we are solving a lasso. So that means what, by solving this lasso, what it is doing is, if the treatment di is dependent or is impacted by some of these or a few of these things, I mean the potential predictors, then that relation will be brought out here. That is, it will be able to identify which all things or which all of the factors are impacting the treatment di, so that we can identify them. So even this is not going to be enough if these xi prime, the problem, that is to say the factors here, if they themselves are further related to each other. In that case, we may actually need a triple lasso or a quadruple lasso and so on. That is in that case, what will happen is that we will basically have to take all the p+1 potential factors, like two at a time, and see whether there exists a causal relationship between them or not. That is to say, first we take x1 and x2, and we see that if x2 can be expressed as a function of x1, as a linear function of x1. If yes, then that means that these two causes are like, I mean, these two potential factors are themselves related. So we do not need to consider both of them together. Maybe we can use only only the one which can be called an effect. That is, after that we will have to consider x3, and we'll then have to see that does there exist a relation between x1 and x3? Does there exist a relation between x2 and x3? And then so basically it will, like, we will have to construct something like what is known as a causal graph, and it will, that is to say, the problem will become really complicated. But as of now, let us not go into so much of complications. Let us just assume that there is the other things we are not interested in. We are not really interested in whether what kind of causal relationship exists among them. We are interested in only one particular causal factor, di, that is the treatment. And what the question which we want to answer is, does di have a causal relationship on yi or not? All other factors remaining unchanged. Okay, so that is why we express this like in term, we do it as a double ML. Again, this will work only if there is only one treatment which I am trying on, from which I am trying to see whether it has a causal impact on the outcome or not, on the final outcome or not. If there were two such things, then double ML will not do. I would probably need triple ML and so on. Okay, it will become more complicated. But as of now, let us keep it simple by assuming that there is a simple treatment. Okay, so now let us quickly take a look at some economic problems where these concepts have been applied. So let us consider this problem of predicting poverty from mobile phone metadata. So what is it? The problem, again, this paper, like I will set an assignment question related to this. So what is happening is or what is the question here is that there is one country called Rwanda in Africa, which you may have heard of. It has a small population of about 1.5 million people. Okay, so you can understand how small the country is. Now it's also a very poor country. Now that is it is what I want to do is I want to get an estimate of the poverty or wealth distribution among these people in that country. So one way to such an estimate will be, of course, to do a survey. That is, I go to like every person, ask them questions about what assets they have, etc., etc., and then we note down all the details. But let us say that this country is too poor and also too inaccessible to carry out such a door-to-door survey. So what has to be done in such a situation? What has to be done is we have to access what is known as proxy variables. What is a proxy variable? Those who have studied economics, does anyone want to give an answer about what is a proxy variable? Anyone has not? No one has heard what is a proxy variable?
Sir, some variable that can give idea about the variable that we are investigating.
Right, exactly. So exactly, that's the correct answer. So suppose I am trying to measure a particular variable called y, but for whatever reasons I am not able to measure y directly. Then what can I do? I measure something called z, which is which is easy to measure and which has a direct relationship with y. That is to say, there exists a function f such that yi is equal to f of or y is equal to f of z. Now that function f I may not know, but I am reasonably confident that such a function exists. Okay. So if that is the case, then I can say that z is a proxy variable for y. That is, even if I do not know y, if I measure z, or even if I cannot measure y, if I then measure z with the help of the function f, I may be able to find y. Okay. So in this case, the proxy variable which this study has considered is mobile phone related data. So that is like India, which so we know that a particular feature of India is that India has a very large number of poor people, but India also has a very large number of mobile phone subscribers. And mobile phones are also used by many poor people. The similar situation holds by in Rwanda also. However, the behavior, the way people behave using their mobile phones, that may vary from person to person depending on their economic status. So if we can somehow access the mobile call records of all the subscribers, then that can give us some kind of an idea about their economic or about their economic prosperity or about their poverty. That is so in this case, we can say that y is the thing which we actually trying to measure. That is to say, the economic condition of every person in the country, but that we are not able to measure directly. So we are taking the help of the proxy variable called z, which is the mobile phone metadata. Okay. And the assumption is what? The assumption is that there does exist some kind of a function f which can map z to y, the mobile phone call records to poverty. Again, that is what kind of a function is there? That's a different question. So for that purpose, to estimate that function f, what we do is, what they do is they actually collect a small sample of people. Maybe some people who are whom they have been able to access in some way. So that's a small enough number, 856 people they have taken in this study. Okay, but they have made sure that these people are chosen at random. This is the, again, as we are talking about randomized control trial, this is also precisely what they have done. They have taken a random sample of the people. So so when we have taken that random sample of people, can you guess what we do with this random sample of people? Yes. So for these randoms, that is again, let me repeat the question. I am trying to measure y, where y is the economic condition of every Rwandan. So if we consider any Rwandan person I, then we are interested in measuring y, which is their economic condition. Now we are unable to measure that directly, so what we are doing, we are accessing their mobile call records. Let's call that as ZI, the call records of the ZI person, or various metadata related to their mobile phone. Let's call as ZI, and our assumption is that there exists a function f such that yi is equal to f of ZI. Okay, but I do not know what is the function f. Now I am telling you that what these people did, the researchers did, is they collected a random sample of these people, 856 people from Rwanda. Now using your common sense, please try to tell me what they did using these sample of 856 people.
Determine the function.
Determine the function. Okay, fine. That's a very good attempt. So So if we have these people, what can we do with these people? So since we have got this sample of people, from them we can measure YI directly, because it's a door-to-door survey of 1.5 million people may not be possible. But since we have taken these 856 people, we can find a measure YI from them. And ZI also we know from them, that is we know the ZI of all the persons. So for these 856 persons also we know. So as was just said, we now for these few people we know both YI as well as ZI. Okay, so now what can we do? We can now try to estimate the mapping F from ZI to YI. Okay, so now this now what is ZI? Now ZI is the mobile phone related metadata, which now that can be like a very large number of such metadatas can be there. For example, how many calls they have made on the past 30 days, or how many calls they have made in the past 1 year, how many contacts they have, what is the duration of each call, or maybe who are the other people they called, then how many text messages they send, how many text messages they receive, then like what about the mobility of the phone, like does it stay in the same place or does it roam around? So many possible metadatas are there. Let us say that they can get some for every person they can get some 1000 pieces of metadata related to the mobile phone. Now, obviously, not all of those features or all those pieces of metadata are going to be useful in predicting their economic condition. But I do not want to be judgmental about which features are going to be useful and which are not, because there may exist some unusual or counterintuitive relation which I had not thought of. So I do not make a judgment on that. I let it to be figured out from the data. Okay, so then so what is the machine learning problem here? The machine learning problem here is you build such a function or build such an algorithm F, which given Zi will be able to predict Yi. Okay, so and essentially this becomes something like a feature selection problem. That is because, as I said already, Zi, the mobile phone related metadata, is is quite large. Like there are maybe 1000 pieces of metadata, out of which only a small number of them is useful. So basically, this is exactly the same as the feature selection problem which we were talking about earlier. Okay. So now what do? We run a machine learning algorithm which allows me to select those features. So what can be those machine learning algorithms? One is definitely the lasso regression, which we talked about. Okay, so that's a feature selection problem. What else can there be? There can be decision tree, which we studied in the last class. Okay, so what is so just to come back to decision tree, I think we in the last lecture we had not finished decision tree. We had stopped at decision stump. So what is a decision stump? Decision stump is basically the process in which you have a data set including a number of features. Now what we try to do is we try to understand which features are informative and which are not, or which features are discriminative, which are not. Discriminative means what? Discriminative means helps me to predict a particular the output y which I am trying to look for. And again to recapitulate, so say for example in this particular example here, so that is the output variable is y. What we are trying to predict is whether it takes a high value or a low value, and for that so we are basically taking each of the features and seeing that by varying that particular feature does the probability distribution of y change or not. So if company is C1, then it turns out that the probability that it will get that particular camera will get a high rating is quite low, 0.2. But if the company changes to C2, pardon the typo here, then that probability of getting high rating increases from 0.2 to 0.55, which is a drastic increase. So we can call that say that this is a discriminative feature. If we consider this price, then whether the price is low or not, it seems that the probability of high rating remains the same. So that is, the probability remains unchanged. So we can say that price is not a discriminative feature, and so on. So the task is here, we are trying to select those features which are discriminative, that is, which help me to predict the value of y. How do I measure discriminativeness? That is through the quantity known as entropy. For every feature, I carry out or I measure what we called as information gain in the last class. And this information gain is basically the reduction, is a measure of reduction of entropy. If we have the full data set had some entropy. That what is entropy? It means that is, the more the entropy, less the information. When entropy is basically a measure of randomness. If a set has high entropy, that means that set contains a lot of uncertainty, a lot of randomness, and hence it contains low information. So now what I try to do, I have a large set with a lot of uncertainty like this. That is, then what I do, I split it. I split it into two smaller data sets, and I try to see whether those smaller data sets have less randomness or not. That is, they have less entropy or not. And the reduction of entropy from the original data set to the split data set, that is known as the information gain, whose formula is given here, right? So the higher is the information gain, that is, if I split the data set with respect to a particular feature, if the information gain is high, that means that feature is discriminative. It is helping me to come to make a decision about y, which was not the case if I did not split on that according to that feature. So I did, so even decision, what we do in case of a decision stump is that we have the original data set, we select that feature which gives the highest information gain, and accordingly we split the data set. Now, so how does it help? So now the thing is, if we get a new example, a testing example, we can focus on that particular feature on which we split, and we then decide whether the test example belongs to this part of the split or that part of the split. And whichever part of the split it belongs to, since this split is much less random compared to the original split, original set, that means what? So that means we are able to confidently predict a class level for this. So as we had seen in the last Friday's example, sorry, last Monday's example, like if the camera company is C1, the company of a particular camera is C1, we are more or less confident that it will get low rating. How confident? Now 43 by 54, that much confident. There are 54 cameras with y which had y equal to L, that is, which had the company C1. Out of those 54, 43 got low ratings. So 40, I am confident with a confidence of 43 by 54, which is like more than 70%, that or actually which is like 80%, that this is indeed going to get low ratings. If on the other hand, if the company is C2, then I am about 55% confident that it will get high ratings. Okay, so that way I can make the prediction. So whenever I get a new camera, I look at its company. If the company is C1, I can confidently predict that it is going to get less rating. And if the company is C2, I can less confidently predict that it is getting high rating, right? And then, so then the question is, so what is the measure of the accuracy I can achieve by using this kind of a classifier? So so as you can see, there are 100 examples, okay, which has L of which have got 63, that is low, so 63 of which have got L ratings, and 37 of which have got high ratings. So out of those 63, now 43 are here, 20 are here. Now everything that is here, that is belonging to company C1, I am predicting that they will get low ratings. Everything that is here under company C2, I am saying will get high ratings. So how many of them are actually correctly classified? So it turns out that 43 of these have low ratings, and I am predicting low ratings also. 26 of them have high ratings, and I am predicting high ratings also. So these 43 and these 26, total 69, they are correctly classified. Their ratings, their actual ratings are equal to their predicted ratings. These 11, they have high ratings, but because they lie in because they belong to company C1, I have predicted low ratings from them. So these 11 are misclassified. These 20, they have got low ratings, but because they belong to company C2, I have given them high, that is, I have given them high ratings. So they are also misclassified. So 69 are correctly classified, 31 are misclassified. This is the decision stump algorithm. Now this is, so basically what I did here is I identified the most discriminative feature and I split the data set based on that. I built up a classification rule based on that discriminative feature. Now what about the other features? The other features are less discriminative than the first one, but maybe they can still help. So now what do? We now that is, by splitting the original set, we got two subsets, right? Now what we can do? We can try to split some of these subsets also. So now what we are doing is, say we are considering another feature, that whether the price of that camera is less than $500 or higher than $500. Okay. So here we are seeing that there are among the cameras belonging to the class C1, 54 of them are there. It turns out that 50 of them that is are cheaper than $500 and 4 of them are more expensive. And it turns out that out of those 50 which are cheaper than $500, 40 of them have low ratings, 10 have high ratings. Among these, and only 4 are here, among them 3 have got low ratings, 1 have got high ratings. Now you come to this part, the remaining cameras which belong to company C2. Again here, this subset we apply try to split in the same way. There are 46 here. I find that 40 of them are cheaper than 500. The remaining 6 are more expensive than 500. Okay. So now what do? We find that among these 40 which are cheaper than 500, 25 of them have high ratings, but among the ones which are more expensive than 500, 5 of them have low ratings. So this is how, so now we have like a double criteria, right? We have that is, we have, first of all we look at the company feature, next we look at the price feature. Okay. Why now the question might arise that why am I going for this feature? Why not say some other feature? Why not go for the video rate and so on? I may go for that also. The answer, simple answer is, I will try to look for information gain. I have already split the initial data set with the respect to the first feature, which is the company. Now the split data sets also I am trying to split further by focusing on the other features. Okay, and whichever feature, just like in this case, just like when I was trying to split the original data set, here also whichever feature gives me highest information gain, I split according to that. So this is the decision tree algorithm. Identify the feature that results in maximum information gain. That's the first step of your decision step. Split the data set accordingly. Identify if any feature can result in further information gain on the split sets. If yes, if there is some other feature based on which you can split these subsets further, right? Then if such a feature exists, then you split it. If it does not exist, stop. Now, if you split it, then you go back to step 3. That is, you identify for more features also. Can you? So now you have, so earlier you had initially you had just this set. Then after splitting on company, you got these 2 sets. Now these 2 sets also you are further splitting and like this, and now we have got 4 sets. Right? Now you may be tempted to ask that, will I stop here or will I want to split them even further? The answer is to that is, of course, whether is there any feature which is giving you information gain or not. If yes, go ahead, split it even further. If no, stop. Okay. So this is like, and then once you have been able to, once this process of splitting has stopped, then the different subsets which you have got, we call these as the leaves, the leaf nodes. So the like I am sure you have all of you know what is a tree data structure. So these are basically this is such a tree is called a decision tree. Why is it called decision tree? Because every branch of it is associated with a decision. Is the company C1 or is it C2? So you have to make a decision here, accordingly you take a branch. Similarly here also you have to take a branch. So finally the set which you have got, where there is no further splitting is possible, these are the leaf nodes of such a tree. And in each leaf node a number of examples exist, out of which will, and these examples will of course have different class levels. So what will you do? You will select whichever is the mode level. That means what? What is mode level? So here you can see that there are 50 examples here, out of which 50 examples, each of them have a level. For 40 of them, the level is low rating. For 10 of them, the level is high rating. So what is the modal level here? Modal level is that level which has highest frequency. In this case, the answer is L. So similarly, if you consider here, what is the modal level?
H.
H, because it's like here its frequency is higher. So here we will use this as the prediction. Okay. So how do we? So now we have built a decision tree like this. So the question is now we have got a test case which belongs to company C2 and its price is $350. You now predict what it's whether it will get high ratings or whether it will get low ratings. So what is to be done? First, we do not have any information that is any information about its features. So the test example is just one of the many other examples. Then what do we do? The tree tells us consider its company feature. What is its company? C2. So we come to this subset, the subset of those examples which belong to company C2. Now what our decision tree tells us? Check whether its price is less than $500 or more than $500. Its price is $350, so less than $500. So we come to this subset. What do we find in this subset? We find in this subset that the modal level is H, right? So, and there is no further split to be made, no further feature is to be examined. So what we do? We simply predict y is equal to H. Okay. So this is the way our decision tree algorithm works. So this is of course binary classification, that is there are only 2 levels are possible, either low or high, but in general it can be extended to multi-class classes also. That is at every, the idea remains the same, at every leaf node you simply count like which is the modal feature, which is the modal level, that is which level has the highest frequency, and you make the prediction in that leaf node. Okay. So this is what our decision tree does, and this can be extended to regression problems also. What's a regression problem? Regression problem is such a problem where the target variable y which we are looking for is a discrete variable. Is a continuous variable. So since it's a continuous variable, So like you will not have like you will not be able to measure frequencies like this. It's like saying that in this case we are what we are doing is basically we are measuring the frequencies of the different labels. But if the labels were real values, then probably there will be no examples which have no two examples which have the same label. So we will not be able, it will not make sense to measure the frequencies in that case. So what we will do? The answer is, when we are making the final prediction, instead of going for the modal level, you simply go for the mean value of the levels, right? That is, they are real numbers, so you can take a mean of that. An example, and the another difference if we are going for this this regression is that you in that case you cannot go measure the entropy. Entropy does not make sense. Why it does not make sense? Because entropy we defined in this way. How we define entropy? Entropy we defined as, basically we have a probability mass function like this. Like this. We have a probability mass function which takes say k different values for and which we call as say p1, p2, p3, p4 up to pk, and each of those probabilities we for each of those probability values we calculate this and we get the entropy value. Now so we are assuming that this can work for a probability mass function which takes k different values, right? But that makes sense if it's like in a classification problem where the label takes the label variable, it takes k different values. But in case of regression, they will all take different values. There is no two examples will have the same level. So we cannot have a probability mass function, right? We all know this. When we are going for a when we have a discrete random variable, we have probability mass function. But when we have a continuous random variable, we have a probability density function. In this case, of course, trying to fit a probability density function is more difficult. So we will not go into that. We do not do we need to. The only thing which we need to do here is we need some measure of dispersion. That is or some measure of homogeneity. So high entropy means what? High entropy in case of a like in case of the classification problem, high entropy means different labels have high, or several levels have reasonably high probability. It and low entropy means which means homogeneous. So high entropy basically means heterogeneous. If there are multiple levels which each of which have high frequency, say one has 30% frequency, another has 40% frequency, etc., that means there is a significant amount of heterogeneity. But if one level dominates, that means there is homogeneity. Most of the examples have the same level. So in that case, maybe 90% of the examples have one level, the other 10% have another level. So instead of so that is basically the entropy is basically a measure of the heterogeneity or homogeneity. If the entropy is high, that means it's heterogeneous. Entropy is low means homogeneous. So in case of regression, as I said, in case of continuous values, we cannot measure entropy. So instead of measuring entropy, we simply measure the variance. Variance is what? Variance is a measure of dispersion. If we have a homogeneous sample, will its variance be high or low? Yes. Does a homogeneous sample have high variance or low variance? Hey, come on, this you have to know.
So low variance.
Low variance. Low variance, right? So a homogeneous sample has a low variance.
No.
Heterogeneous sample has high variance. So whichever that is, so what we try to do here, instead of measuring the entropy, we try to measure the variance. Whichever, and we try to split the data set according to that feature which reduces the variance. which instead in case of classification we try to reduce the entropy, in case of regression we try to reduce the variance. So whichever feature reduces the variance the maximum, you choose that feature for splitting. So for example, in this example here, if you look at the this company feature, that is like here, if we are going, that is we find that the reduction of variance is 0.06. That is, the initial variance was 1.1. Okay, when we did not split the thing, when we had full 100 examples, the variance of the ratings was 1.1, let us say. Now let us focus on those 54 cameras which belong to camera C1, company C1. For them, the variance of the ratings was 1.5, which is a much larger variance, which means that the this whole thing becomes more heterogeneous. In this case, if those which are in company C2, we find that their variance of their ratings is 0.5, which means it's a homogeneous. So we take a heterogeneous set and we split it according to the company feature. We get a subset which is even more heterogeneous and another subset which is more homogeneous. So now we measure the total reduction of variance, which comes out to be 0.06. Now this is so that's with respect to the company feature. Now we come to the video rate feature. We try to split it according to this video rate feature. We find that for those examples for which the video frame rate is less than 30 frames per second, the variance is 1.2, which is pretty much same as what it was originally. And for the remaining ones where the video rate is higher than 30 fps, here I find that it is homogeneous. Its variance is much less, 0.4. So that means what? I started with a heterogeneous set. On splitting it with respect to this feature, I found an equally heterogeneous, slightly more heterogeneous set and a significantly more homogeneous set. And if I measure, we find out that the reduction of variance is 0.14. So I definitely choose we see that the second feature has given me a bigger reduction, so I can go for it. So this is what how a regression tree will work. Okay. So now coming back to the example, like if we see this example, we find that this decision tree, be it the regression tree or the decision tree, it basically enables us to choose the discriminative features. So here again we had a set of so many different features which we are talking about here, maybe some 1000 features based on the phone metadata, out of which most of them were useless. Now by running an algorithm such as lasso or double lasso or decision tree or regression tree, depending on whatever is suitable, I am able to identify only the important features. And then we are able to, then once we have identified those important features, then we are able to make the predictions. So the training is done on the basis of only these 856 examples for whom we know both Y and Z. But as somebody already said, using these 856 people, I estimate that function f. Now that function f, that can be a decision tree, it can be a lasso regression, or it can be something else also. Okay. And once I have estimated the function f, then I can run it on the Z collected from all the 1.5 million mobile phone users. As I said earlier also, I do not have access to their economic records, but I do have access to their mobile phone records, their Zs. So now that I have got f, then I can run this f, or I can apply the function f on their Zs, and I can predict their wealth indexes. Okay. So this is basically the study they have got. They have got a geographical distribution also of the wealth indices. So for every person whose call record I have accessed, I know where they are geographically located. So, and then I have their wealth indexes also I have predicted. So if I plot the wealth index as a map, as a spatial map, then this is what it looks like, and we can see that there are some dark regions like where the predicted wealth index is very low, means that these are the poor regions, and then there are some other regions where the predicted wealth index is quite high, suggesting that these are the rich regions. And so this is the prediction which I have made, and then once I have made a prediction, of course I have to validate it. So that is validated with the help of against some kind of region wise survey. I mean, a person to person survey could not be done, but maybe a region wise survey is possible. And it turns out that this spatial map actually perfectly resembles the region wise survey results which has been done. I mean, those regions which are known to be poor are shown to be predicted to be very poor also. The regions which are known to be relatively better off are predicted to have a higher wealth index also. So we can assume that what we have done is a good prediction. So just to summarize, the first step is feature engineering, where we have to transform the basically access we have to get their call records and use those call records to calculate the different metadata which we are talking about. So I was talking about 1000 metadata. So actually what they have created some 5888 metadata. For every person, so many pieces of metadata are there. These are all their potential predictors. The second step is feature selection, where they try to, out of these, so all these 5000 odd features, they try to select only a small number of features which will be useful for their wealth index prediction. Okay, and once we so as I said, I was telling earlier, like if we do a scatter plot between the predicted wealth and the actual wealth obtained from some kind of a survey, we find excellent correlation between them. Means that we have been able to very well predict their wealth indexes using their mobile phone call data. Okay. So yeah, so basically that's a case study which we considered here. There, like I have shared, like if you this is a set lecture from University of Oxford by Michael Coel, who is an economist who is using machine learning methods. So in the files folder of these teams, this is there. So I request all of you to go through this document. It's very well explained, and more such examples are there. For example, consider this another example. Here what we are trying to do is, here we are trying to predict successful entrepreneurs. For different people, we are trying to predict whether they will be successful in their business ventures or not. So which are the factors that are important to predict that? That's a study they have done specifically in Nigeria, and there are more studies like that. Another set of things another set of lecture notes which I have shared in this folder, which I will not get a chance to discuss, is this lectures by Esther Duflo. Have you heard of Esther Duflo?
Amartya Sen, right?
Yeah, sorry.
Related to Amartya Sen.
No. Okay, related to yeah. So Esther Duflo is a Nobel laureate in economics. She won the Nobel. She has done she won the Nobel Prize in economics in 2019. She is not Amartya Sen. She is the wife of another Indian economist, Abhijit Vinayak Banerjee. Both of them, husband and wife, won the Nobel Prize in economics in 2019 for their work on randomized control trials. So these lecture notes I have shared with you. Please, I would encourage all of you to go through this. So here also this concept of double lasso is explained in detail and with some case studies. Okay. So I am sorry to take this class so deep, 20 minutes past time. But we really have to, I really wanted to make sure that you are following. So that's why I decided to recap some of the things which we have already done. So fine then. So tomorrow we will look at a different topic, and after that we will see we will try to see some more case studies of this. Okay, thank you for your patience.
Thank you, sir.